Hey everybody, they're currently working on pressure washing Haslam, and I keep saying, I'm just like, I'm not breathing it in. Anxiety. Anxiety's fun. Anxiety's fun. Anyways, less anxiety in the world would be good. Less anxiety would be good. Less anxiety. With that said, I might do some review right here because I want to point out the formula sheet. I think Mubot's awake. Pulp review 2 right here. Pull up the formula sheet. Get Mubot loaded in. What's up, Mubot, in the chat? Let's see. Okay. Formula sheet. Let's go look over the formula sheet. Here we go. Oh my gosh. I'll be right back after these messages. Okay, we're back for the moment. Let's go talk about reviewing for the test real quick here. So with reviewing for the test, let's pull up today's office hours. With reviewing, let's talk about it. There are things you have to know. So chapter 7 review. So what I want to point out right now is the speedruns are going to be your number one way to know how to do the test. Knowing the information on the speedruns, and of course we can talk about some of it here. You have to know these formulas. You have to know what they stand for. You have to know the notation. If you don't know the notation, then it's going to be a lot tougher of a test. So here we are on the formula sheet. What do these quantities even mean? So we got regression right here, and that is the predicted value from an equation. So y hat is predicted y. And b naught is going to be the intercept, and b1 is going to be the slope. And with this right here, x is the x variable of interest, or sorry, the x variable that's the explanatory. And then we have e equals a residual. And then y is going to be the actual. So you can see when it comes down to this, I don't have speedrun saved right there. And sorry, they're doing things outside and it's causing me distractions. But the notation is going to be essential to this. And if you don't know the notation, once again, the test is a bit harder. Going over to the studio, I highly suggest watching the speed runs here. Oh, it does not have most recent videos? Content. Analysis. Analysis right here. Chapter 7. Oh, people are watching the Chapter 7 speed run. Okay. There was a good bit of views yesterday. Views are starting to happen more today. And people are starting to go through the material. It's this. I really believe in the speed runs. I really do. And it's interesting to see how many views there are. But watching them, trying to understand them better, because you can only learn so much in so much time. You have to take it in over little bits. You can't just be like, I'm going to learn it all tonight. I'm going to learn everything. It takes time to learn this material. It takes time to practice it and actually get the material down. You can't just learn it all at once. You can see the probability right here. We'll just call this section reviewing for the test. Reviewing for the test. What reviewing for the test? Where'd it go? It says one's watching. One. Reviewing for the test. So, once again, when you are, I was going to say once again a lot. I think this section right here is usually where people have problems. This section is where people get confused and they don't know how to work a problem. So let's create a fake problem right here. Let's create a fake problem. And we'll call this fake problem. Okay, we're opening up the screens. And you should be able to see just a second here. You should be able to see the screen. Okay, so if you got a problem on the test, it's the following. Let's say see, no one's in the chat. No. Do we pass the success failure condition? Do we pass the 10% condition? So with these conditions right here, there are specific ways to check them. So the success failure condition for categorical data must have at least 10 successes and at least 10 failures. So that's what it is. It's for categorical data only, which this is just a qualifier right here. It's not like part of the condition. It's not like must be binary. That's not what it is. But used for categorical data. So the first thing to do is find your n, find your p, find your q, are np and nq at least 10. The 10% condition must sample less than 10% of the population. So find your n, find your capital N is n divided by capital N less than 10%. So with this right here, we can check these conditions. Let's take a look at our problem. We actually don't need the equations for this. We'll bring them back here in a little bit. But with this, you want to identify notation. It is known. So we'd go right here. We'd identify n. N is the sample size. Remember, n is sample size. Capital N is population size. So that's how many are made a year. And the proportion is 3%, so it's 0.03. So P equals 0.03. Q is the complement of P, 0.97. So that is P, that is Q. And we've identified pretty much all the notation in this problem. So we can see if we pass it, there are the answers, the questions, or to the questions at least. So we actually don't pass the success failure condition because 100 times 0.03 is equal to 3, which is not big enough. So this one actually fails. You can do 100 times 0.97, and that is equal to 97. So this one actually passes, but they both have to be at least 10. And then this one right here, we do 100 divided by 50,000, and that is going to equal to, I think, 2% of the data. Is that right? Oh, is it 0.2%? Check our numbers. 100 divided by, there it is, 0.2. Yep. So it's way less than 10%. Way less. That is 0.002, which is less than 10%. So we're actually good on this condition. And just knowing these little things right here, how to check the success failure condition, we wouldn't do the large enough n for this because it's not quantitative data. But knowing how to check these conditions are very important. You do get questions that basically just say, is the condition passed? And you have to identify the notation. So these steps right here list for you each way to do it, and just simply check the conditions. So now we would have problems like, no longer checking conditions. Is it unusual that in this sample of, here we'll change this because we failed a condition. We're going to a higher failure rate of 15%. We work at a very bad shoe company. Is it unusual that in this sample we had 18% defective? Give a z-score for justification. So when you get a problem like this, you need to know the notation, and let's go grab it. We have it on the formula sheet. So sampling distributions right here. We actually only need the top one. The top one's for categorical data. So we go back over here and we drop it in. So solving a sampling distribution problem, you basically always, for any problem you're doing, want to mark your notation. And then with the notation marked, you want to go in and solve the problems. So we mark our notation, figure out if it's categorical or quantitative. So we know that capital N, which is population size, not used in the equations, but used to check conditions. Lowercase n, which is the sample size. The proportion of successes, which is a defect here. The proportion of failures is the complement of that. And I just made a mistake. And then the observed proportion of failures, which is p hat. And technically, we don't need the observed proportion of the other side of it, but we could. It won't be used in this. Now, if you look, the equations do this. They walk you through what is mu p hat, which is what we'd expect to see in a sample. So we would expect the sample proportion of a sample, sample proportion of a sample, the mean of a sample proportion, excuse me, to be the true proportion, which is p. So we simply expect in a sample to see 15% defective. We expect the standard deviation of the sample proportion to be p times q over n square root. So we type in p times q over n square root. That's what we do right there. And now let's find that. I'm not blocking it yet. 0.5 times 0.85 divided by 100 and square root. And sampling distribution. So there it is, 3.6. I'm rounding it. And then we simply plug it into the equation over here to see if it's unusual. And that means we take the proportion from the sample, which is p hat, minus the true proportion. So we're doing p hat minus p over standard deviation of p hat. And this is equal to the following right here. and then we just take the standard deviation. It's less than a standard deviation above. So this is going to be a not unusual z-score because a standard deviation is that, and that's only 0.3 above. If you notice here, this is 0.03, and we're dividing it by 0.036. So that is going to be like 0.8 or so. So we take 0.03 divided by 0.036, and there it is, 0.0833. So z equals to 0.0833 repeating. And on a curve, that would look something like where you go up not even a full standard deviation. So you'd go up not even one, and you'd land about here. So that's about 20% of the curve. 20% of the curve, which means it's pretty usual. It's not an unusual occurrence. We can go over to the apps and get the exact answer. You would not do that on the test, but you would say a z-score of 0.833 is not unusual. I estimate about 20%. So on the app, which you won't have on the test, you would go here and do above 0.833. And whoa, I lucked out on this exactly. Very close to 20%. So my estimate of about 20%. If you look at this drawing right here and mine, they should look kind of similar. That's what you want to do if you make a little quick sketch, is you'd make a similar drawing where it's not even a full standard deviation above the mean, which is not unusual. Z-score outside of 2 or 3 is unusual. Let's take another version of this problem, but do the sampling distribution of the sample mean, because this is where people get confused. Okay, so when you get a problem, you want to first look at it and see if it's categorical or quantitative. So that's where people get really confused on this last chapter. And this goes to how to do the homework. Okay, so 1803, example test problem, how to work sampling mean problems. So for any problem you get on the test, if it's a sampling distribution of the sample mean, it'll be quantitative. Like, let's say a waiter knows that they get on average $10 at a restaurant per table. They want to make $500 this weekend off of 50 tables, 40 tables, off 40 tables. They have a standard deviation of their single tips of $7. The distribution of their tips is slightly skewed to the right. Question 1, do we pass random? Question 2, do we pass less than 10%? Question 3, do we pass large enough n? So let's explain how to do this and check each condition. Well, random can be debated here because it's like, is it random? This is where some people might say, I don't really know. This question is not clear. Wouldn't make a good test question. It'd be a good written test question, but this one is like, I don't really know because it doesn't state it's random. And people coming to a restaurant, if it's like the weekend, are not truly random. There's arguments against it, and there's arguments for it to say, well, it's just a random assortment of people who come to the restaurant. Do we pass less than 10%? So remember, we need to ask if this table of 40, which is the sample size here, is less than 10% of all tables they can wait on. Well, this is pretty much infinite. There's pretty much infinite people who could come to the restaurant, theoretically speaking. So I would say that this is definitely passed because this is a very large amount. Like, there's more than 400 possible tables that would come into the restaurant during any given weekend for all restaurants, for all people. So they've probably sampled less than 10% of all people who come into restaurants. So we're good there. Do we pass large enough n? So to pass large enough n, this is where people get confused. Large enough n. What you have to do for this one is first, it's used for quantitative data distribution of sample mean. The first step is, what is the shape of your data? What is the required sample size? The last step is, do you have this sample size? Okay, so we need to find the shape of our data. Well, first, there's 3 general shapes you generally see: normal, skewed or very skewed. And the required size for these are 1, 25, and 100. If you notice, our data says that it's slightly skewed, which falls more into this, which means we need at least 25. And it's important to know what this is going to do because according to the central limit theorem, the distribution of the mean will become more normal as n increases. So remember we're saying our distribution is slightly skewed, like we have right here a slightly skewed distribution. And if we take a sample size of at least 25 and find the mean of these observations, we'll get a new distribution down here for the mean. And if we keep doing this, you'll see we get a mean for each sample of size 25. That means we'll eventually build a distribution which is normal. And I know it's crazy, but if you don't have a large enough n, it's not normal. And you can get really skewed distributions, like crazy looking skewed distributions that are even more skewed with maybe outliers. And now you notice it's even less normal. But the larger n is, the more it normalizes the distribution of the mean, not the original data. So also it gets tighter and the mean stays the same. This 8.14, I know it says 8.15 there, but watch this. Enough clicks, there we go. Enough clicks and it'll go to 8.14. We can actually calculate the standard deviation right here. The standard deviation would simply be divided by 5 because it's the original standard deviation of the square root of 25. 8.57 divided by square root of 25. And there it is right there. It says 1.72. And it will eventually round down probably if we do enough simulations. It's just, you got to really simulate a lot. Oh my gosh, please round down. 5, 4, 3, 2. That's not enough simulations. 1. Well, there's a lot of decimals right there going on in the background. So, but a little more simulation, maybe we would get it. Okay. So this meets the large enough condition because our sample size is 40, which is at least, it's greater than the required sample size. So we meet it. So other than random, you might say this problem's great. There's the large enough n condition on how we pass it. And now the question might say additional things right here. Is it unusual, or what is the probability they make at least $500? What do they make on the best 5% of their weekends? So a lot of the My Pearson questions do this to you, but they don't give you the steps. So if you don't know the steps, you get stuck on this because you're like, well, what do I do with this information? Well, remember, we have the notes on what we're supposed to draw out right here. So here's the sampling distribution of the sample mean. There it is right there. And we go back over here and drop it in here. So we need to, before working any problem like this, go ahead and start solving this. And notice we need to get the notation again. So it says they make on average $10, and it says they know this. Since they know this, this is the true mean. Next, it says they want to make $500. Well, that's going to be the sum of their tips. It'd be the sum of their observations. All 400 tables are 4D tables. So that's going to be the sample size n right there, which we could also mark down here as sample size. It says the standard deviation is 7. There you go. And I think we have a lot of this in here now. And now we need to find y bar. So y bar is what they need to make on average. So to find out, we simply take the sum of the observations and divide by n, which is going to be $500 divided by 40. And that is equal to, they need to make on average, y bar equals $1, no, $10, $12.50, my gosh, the math broke. $12.50 right there. I'll use take 500 divided by 40. Should be, no, yeah, it is. Let's double check. 500 divided by 40. There it is. So that is correct. That's what they need. If they make that on average, they'll make $500 this weekend. And so now we need to just solve. Well, mu y bar, which is the mean of the distribution, is equal to mu. So that's 10, because literally it's in blue up there. Standard deviation y bar is equal to the original standard deviation of 7 divided by square root of 40. It's going to be close to 1, but a little bit bigger. It's going to be like 1.12. Let's find out. 1.12. 1.11, and you want to carry the decimals on this one. But we're going to carry the decimals over here. So 1.11. Close enough. And then you simply find out if it's unusual to make 1250 on a table on your tables on average, which is a difference of 2.5, and divide by 1.11. Ooh, it's more than 2 standard deviations. So it's going to be, if you look at where it's at, didn't draw my normal curve right. So it's over about, it's going to be right about here. Maybe more there. And so we're going to see an area shaded on the curve, something like this. And this value is here. So it's important to know what goes where. There we go. They're spraying like the windows outside. A lot of anxiety. Could you possibly, yeah, this is a chapter 12. Which one do you want done, Brock? They're spraying the windows and it's causing me a lot of anxiety. Which one do you want done, Brock? Let me know. This is a chapter 12 question right here. So this is the waiter-waitress problem. And you can simply plug in the numbers now. We can plug in the standard deviation. And we can plug in the mean of 10. And then we can find the area above 12.5. And there it is. So that drawing I just made. Drop a question. There it is right there. If you look at this drawing right here, it should look a lot like what we have. So there it is right there. There's our drawing, and there's the answer. So if you notice, there's the second standard deviation. And this will give us the z-score right here. So we could actually use the z-score in the applet. Take 12.50 minus 10 and divide by. So we get a z-score of 2.25, and that's where that's at right there, about 2.25 standard deviations above. Which one do you want to do? What's the best 5% of weekends? So with the best 5% of weekends, the best 5% of weekends is going to be the top 5% of the curve. So we'd go over here, and we'd find x using the p-value, and we can go, it's almost set up right, to the best 5% of weekends. Now, this is what they would make on average, but remember they're working with 40 tables. So what we do is we take this value and multiply it by 40 because that was what they make on average, but it's on 40 tables. Brock, which one? Drop it in the chat. And I do have a video, I think, doing almost all of it. We had big in-person office hours today. Let's see. But that's a full walkthrough problem right there. You want to learn, the biggest thing to learn, which is tough, is how to solve any problem. Like if you learn how to solve any of them, when you get to the test, you'll know the steps. And I think that's what I always want people to learn from working a problem is like, how do you solve this? Like, what are the steps? Like, how do we solve a certain problem? How do we solve a certain problem? Let's go. It starts with a CEO's annual compensation of 800. Yeah, let's do that one. Thank you, Brock. Thank you for being here. Okay. CEO annual compensation. Here we go. Okay. So what do we need for this chapter? There's two big things, two big concepts. So this is how to solve the problem and get it right for all these anytime. So what do you need for these what do you need? Like what do you need to solve this? Don't even worry what's asking. What do we need? What are the components of solving this? How do you solve any problem in this chapter? How do you solve any component? Owen, good to see you. Are you able to find the problem in 500? Well, that we just kind of did that one. Owen, check out just a moment ago. We kind of walked through it. I've got the full thing on here. And we just did the full thing. Owen, thank you for being here. We just went through the full 500. You need to divide the 500 by 40 to find on average it's a 1250 tip. And that's what you plug in right there. Do you see? Does this make sense, Owen, with the notation on the screen where I have the 500 divided by 40 is 1250 on average. So I divided by how many tables to find the average tip that they want to make. So do you see? This kind of points to the first step of all these problems. How do we solve this problem? What is the first step for any of these problems? What is the first step? Yeah, and then you z-score it. Well, the z-score is not the probability. You take the z-score, and then you drop the z-score in and find the area above it. So I did find the z-score. You can use the numbers or the z-scores. The z-score was like 2.23. If you do z-score it, you need to go over here and then go above 2.23. It was about this. It was something like that. And then find the area above. So this was, we took 12.50. 12.50 minus 10 divided by 1.11. And there it is right there. So, but make sure to carry enough decimals. Well, but here's the thing, though. The very first, don't even worry about the problem, though. What step do you notice that I'm doing for all these problems? What step is very important for every one of these problems? At the start of all these problems, don't even worry about what it's asking. Do what to start? What do you notice me doing? Any one of these problems, do this to start. Any one of these problems, notation, and no one knows right there, notation. So it's all about that notation. Grab the notation to start. I might end after this one because I'm like smelling what they're spraying outside. It's giving me a lot of anxiety. I'm sorry, everybody. I know today's been a weird day, and tomorrow's a test, but a lot of anxiety over like just smelling whatever that is outside. Yay! Fun times. So the true mean is this. So this is mu. And the true standard deviation is this, which is sigma. And then sample sizes are this. And those are n. So remember, mu y bar equals mu. So a lot of problems point out that as the sample size gets larger, what happens to the mean? As the sample size gets larger, what happens to the mean? Well, it's mu y bar equals mu. So all you do is plug in. It stays the same. Nice job, Peyton, right there. Yeah, that's it. And sorry, Peyton. Today's been a weird day. They're like spraying the outside of the building with chemicals or something. So we just plug that number in. So the mean right here, 10.31. That's right? There we go. Now the standard deviation does what? As the sample gets bigger, the standard deviation, which is S d y bar equals sigma over square root of n. Well, sigma is the value right here, and n is going to change. So you can see as n gets larger, so for larger values of n, we get smaller values of standard deviation, which is part of the central limit theorem that states that the distribution will get tighter by a factor of the square root of n. Exactly. Great job, Brock, right there. Man, anxiety is a fun thing. And so with this right here, it's, well, basically, does everyone understand what I'm about to do? All we're going to do is plug in this top value. I'll write it down. It really helps, I think, for people to see it when you write it down. So the value is 19889.85 divided by square root of 30. And then you change it to do square root of 50, and then square root of 100, and then square root of 200. So all that's going to change is the bottom number. So 19889. And the problem is you have to square root the bottom number. So that's a painful thing. This is 14.14. Fun number. And then 19889.85 divided by that. And that was 200. I don't know why I did 200 first. Who feels like this is making sense? Tell me if you're lost on this, because I'm doing the square root of 30. And with the square root of 30, then we divide 19889.85 divided by square root of 30. Carry your decimals, don't forget to. And then square root of 50, 50 square root. And then with the square root, is this like number 6? It might be, probably. If it has a table, it's just having you solve and show how to do it. And then, yeah, and then we did the full homework last one, I think. We did the full homework. 100, let's just divide by 10. So you just move the decimals. 1988.99. That should be right. These are simulations, which if you look at these values right here, they will be close. So if you get one that's really off, that indicates a problem. And the mean stays the same. So these values are kind of close, reasonably close to reasonably close. We got it. There we go. Basically showing that the mean stays the same and the standard deviation decreases by a factor of the square root of n. That's what's going on with that one. Exactly. Yep. So you take the n square root on the bottom, and you do this right here. That's got it. There you go. Good job, Brock. This one's very similar. Very, very similar. Which one should we do now? Let's try to do 2 or 3 more. You're welcome, Brock. Brock, thank you for being here. What other ones should we do? We kind of did waiter waitress. Grocery store and waiter waitress are the same. We could do it though. Drop your question before Brian has too much anxiety. I have my door open right now. Got my door open. Which question should we do? Door wide open. Drink some chemicals. I say, Brian, you drink energy drinks. I say, not anymore. Not anymore. A food company? Oh, let's do it. Where's the food company one? A food company. Thank you, Brock. Okay. So this one, what are we going to do first? I need your help. You know it. You love it. You got to say it.
Notation, brother.
What are we doing first? What are we doing first? You know it. You love it. What's the first step? First step is what? You got to do the first step. What's the first step? Always do this first step. What do? Notation. Yep, Brock got it right there. So the first thing we do is we mark. I don't even read the questions. Don't even read the questions. It's all about notation first. So it says right here, the mean weight is this. Well, this is mu. And the standard deviation is this. This is sigma. And then we have different sample sizes. So what we get right here is we get an n of either 936 or 121. The next thing we could figure out is mu y bar equals mu, which is going to be mu. So literally this right here is this quantity. So this is going to be 41, 41, and 41. And then we get to the standard deviation of y bar is equal to sigma over square root of n. So we need to plug in these values respectively. And look at that. They're all perfect squares. And so then we need the sigma. Sigma, need a different color. There we go. And then we simply just plug in. So we take 3 divided by square root of 9 equals 1. 3 divided by square root of 36 equals 0.5. 3 divided by square root of 121 is equal to, I think it's going to be, I could be wrong on this one, 0.27. Let's find it. 0.27 repeating, I think. Square root of 121 is a perfect square, so it's that. And there it is. There it is. It's like a ninth, but weird. Or like it's like 9. There's relationships within numbers, but they're fun. I love numbers. If you notice, the standard deviation is getting smaller because as n gets bigger, standard deviation gets smaller, and the mean stays the same because there is no n in this formula right here. So 1.5 and 2.7, 0.27. 1.5, because it asks for each size right there, and 0.27, because 2 decimals. So then, which of these would be the most likely to be normal? Well, we talked about the large enough n condition. As n gets larger, the distribution of the mean becomes more normal. And we have this up in this applet to show you that if you're only dealing with the sample size of 2, you don't meet the large enough n condition. And this is because we're taking samples of 2 and finding the mean of that sample, and repeatedly doing this. It won't be nearly normal if the underlying distribution is very skewed. So when we do larger samples, it becomes more and more normal, and this is the distributions of means of a certain sample size. So at a larger sample size, the distribution of means, not the original data, becomes more normal. So the answer for which one will be most normal is the biggest one. So the palettes, because regardless of the underlying distribution, it'll become more normal. There we go, Brock. Let's try one more. One more while they spray down Stokely. What's one more? Yeah, notation's all... Oh, Brock, thank you so much. I'm glad to hear that. You're giving me that energy, Brock. Notation makes it way easier. I think if you plot out, like, don't even look at what they're asking first. Just always plot it out. Grocery store. Let's do the grocery store. Thank you, Owen, for being here. Shout out to Owen. You ready? What are we doing for... I need you to say it. I know you know it. Just tell me, and then I'll do it. Let me mark this while you tell me what to do, because once again, as Brock said, makes it a lot easier. Notation, brother. Okay, a grocery store. There's a trick to this one. Not like a huge trick, but we'll do it. Let's do it. Okay. There's trickier notation for it because you're like, wait, what? Okay. The grocery store has a mean of this. The grocery store has a standard deviation of this. Immediately, we have found mu and we have found sigma. They have 309 customers on a given day. Next, they want their revenue, which this is the trick one. So this would be the sum of all their observations to be that. Now, if we want to find y bar, that is going to be the sum of the y's divided by n. Because, you know, like what we're saying here is like, you talk to two people. Now it's hitting my window. Fun. You talk to two people, and two people, their ages are 30 and 35. So you average them together by adding them up, 70, 65, divide by 2, 32.5. So that's how you find an average, is you sum things up and then divide by how many there are. So the sum of everything, they want the revenue to be 9,100. That is the sum of the y's. And you simply divide by the number of observations. So on average, they want from each sale 9100. We're just taking that sum of y, dividing by 309. And that's 294498. 294498. Make sure to carry enough decimals. It doesn't hurt to keep it stored in your calculator. All we're doing is marking the notation on what we have right here before we work the problem. So now we need to solve for our distribution. Mu y bar equals mu. So can anyone tell me the answer for what mu y bar is? Remember, mu y bar equals mu. So what is the answer to this question? What is mu y bar? So can anyone tell me? I'm going to erase this. What should I put as the value here? So what should I put as the value there? Mu y bar equals mu. We're not even really worrying about the question. That's all it is. Great job, Elena. Yeah, that's it. It's 28. Yeah. Because it's to say if on average you make $28, you'd expect to see $28 in a sample. That's the expected sample mean. So if you take a sample, you expect to see $28 because $28 is the true mean. Now we do the standard deviation of y bar equals to sigma over square root of n. And we simply plug in the numbers, 17 divided by square root of 309. And that's going to lead to, it's going to be a little more than one. A little more than one, I say. Like 1.12. 09 square root. No, it's a little less than. It's 0.96 or so. 0.96. 0.97. Darn it. 9671 equals 9671. Okay. So we have our standard deviation. We have our mean. So you know what you do now? You draw your distribution. Once again, you want to go to the applet for this to draw the distribution. You have your standard deviation. You have your mean. And we go over to the applet to draw it. So we still have stored in here this, which is the standard deviation, and the mean of 28. And then we plug in the observation, and we go above 29.4498. And there it is. There's the drawing right there. We found a mean of 28, a standard deviation of 0.967, and the observation of what we needed to make was this. And you can also use the applet to round your answers to 4 decimals, so we can make sure it's rounded. Are there any questions? I don't want to go too quickly, but this should be the answer to the first one right here for the probability of making at least this amount. You won't be using the applet on the exam. If this was, great question, Elena, right there. Thank you for asking. If this was an exam question, it would likely say, what is the z-score? So the exam would probably say, what is the z-score of this? Because you can solve that. The z-score is observation minus mean over standard deviation of the distribution. So we would take right here and do 29.4498 minus 28 over the standard deviation of 0.9671. And we solve out this. So 29.4498 minus 28 divided by this. 1.5 basically. So it's 1 point. On the curve, it would look something like this. So it's going to be a z-score of 1.5. And what you can do is if you had solved the z-score, you can go back to the applet. Those sheet formulas, yes, they're on. Yep. I've got them pulled up right, or I did have them pulled up. They are on Canvas. That is true. Oh, here it is. Yep. So there's the formulas. And then you could go to the applet and enter above this, and you'll get the same answer. Because you can do above the z-score, or you could use the context of the distribution. That's when I draw them. I usually put both number lines below. But does that make sense? So we could z-score it and do above the z-score. And the test would ask you for something like the z-score, or ask, is this unusual? And the answer is no, this is not that unusual. It's within 2 standard deviations. So you could know the z-score. We wouldn't expect you to find the p-value though, because that requires like an applet. But you should know if it's unusual. And the next one asks, the store takes in how much on the worst 10% of weekends. So this is why you need the applet to show the numbers. It's best to have the numbers in here for this one, because now we're switching back where I've entered in the mean that we found in the standard deviation, where we found the mean of the distribution and the standard deviation of the distribution, SDY bar. Not the original standard deviation, but the new standard deviation, which is this quantity right here. I don't want to highlight like that, but it's the quantity that's totaled right there. It's the sigma over square root of n, 17 over square root of 309. So that's the quantity you see right here, and I carried all the decimals on it. Now to find the worst 10% of weekends, we're going to go find x using p, and we're going to enter in 10% and go down here to the bottom of the curve. Now that's what they make on average. So now we take this that was on average, and it's multiplied by 309 customers. So I multiplied whatever this was on average by, I believe, the 309. And so with that, there it is to 2 decimal places. That should do it. There we go. Let's do one more real quick. What's the last one? I'm going to run out of my office. What's the last one? These are tricky problems, but it really boils down to notation. Really boils down to notation. Notation is so huge for these. It's all about notation. Last problem. Thank you, everyone, for being here. Tricky questions. Last problems. A standardized test. Is that in the... Here we go, standardized test. Okay, let's do it. What are we doing first, Brock? Tell me in the chat. I'm gonna destroy this problem. I only got like 15 minutes before class. What do we need to do? Notation, brother. Oh, notation, brother. Right there. I love them spraying my windows. Fun times. Okay. So here it is. Here's the notation. I'm going to write it down as a table, not like that. So we know we have different sample sizes here. A small class with 9 students. A large class with 36. We have mu y bar equals mu. And the mu y bar equals mu for this is going to be that the mean is equal to the mean, because we know that the original data has a mean of 149. So we're specifically looking for mu y bar, the expected sample mean, but it's just going to be 149 because that's what it is. It doesn't change according to sample size. It's going to be the same for this one. And then next we see the standard deviation. It was 8, but we want the standard deviation of the sample mean. So that's sigma over square root of n. And so we just take right here and do 8 divided by square root 36, which is going to be 1.33 repeating. And then 8 divided by square root... Oh, did the wrong one. That's the big class. Divided by square root of 36 for this one, which is 1.33. And then this one is divided by 9, which is 2.33. Interesting? I believe so. There we go. Just make sure that's 8 divided by 3. No, it's 2.66. Rounded up 6.7. We'll do 6.6 repeating. And that one is 1.33. Sounds good. And so now that we know this information right here, it's going to start asking us questions about it. Notice it says that both of the distributions are unimodal and symmetric. So this is going to the large enough n condition. Oh, I didn't timestamp it. Let me mark a close enough time. 4903, stat 201, chapter. 14. A standardized test. Okay, so since it says they're both unimodal and symmetric, that means we're dealing with a normal looking curve. And even if you have a small sample size, the resulting distribution is normal. It's only that we need larger sample sizes when there's a more skewed distribution. If it's extremely skewed, a very small sample size will not be large enough to create a nearly normal distribution. So once again, we're dealing with a normal distribution. So a sample size of both 9 and 36 are large enough. So the distributions will both be normal because they're both normal to begin with. If either group gets a 157, that's a good thing. So let's look back here. Now they're putting in an observation of 157, where y bar is equal to 157. So what we can do is we can run this through the formula. Observation minus mean. I'm going to lose enough room, so I'm going to have to do this. It's going to be observation minus mean over the standard deviation of the mean. And so we'd have to plug in for both of these because we have two sets of values. So we're going to take right here and the top of this. So y bar minus mu is equal to 157 minus 149, which is equal to 8. So the top of this equation is 8. So 8 divided by 2.66, because all we're doing now is plugging in this number. We'll also plug in the other number, because that's the standard deviation of y bar. So 8 divided by 2.66. Ah, man, my brain's too slow today. That's not 3, is it? No way. It's like 2.33. So 8 divided by 2.6. It is 3. Wow. Good stuff.
Wow.
So this would be 3 for the smaller organization. And the larger organization is going to be, we just change the number on the bottom because we're dividing by a different standard deviation. So all we do is plug in that number there, and we divide by 1.33. And with 8 divided by 1.33, that's going to be 6. 8 divided by 1.33. There you go, 6. So 6 and 3. So 3 is less unusual because 3 is over here and 6 is way off the curve. You can't even see 6 on the curve. It's way off the curve. So 3 would be less unusual, and that was for the smaller class. When we plug in the numbers, they had a z-score of 3. So for the smaller class, it would be 3 standard deviations above. For the larger class, it would be 6, making the smaller class more usual. They're more likely. Next is 142. So all we're doing now is changing this value right here of the observation and figuring out its difference. So how far away is 142 away from this? Well, 142 is the observation. The mean is 149, which is a difference of -7. They're not going to use the negative in this. And of course, we got one with decimals. A little bit worried. That's right? So that's kind of similar. It's going to be a very similar problem. We're just changing this, which means it should be a little bit less of a standard deviation. So now we just take and divide by both numbers. Divide by 2.66 first, and then divide by 1.33. And we do this equation right here to figure out the z-score of it. So 7 divided by 2.66, repeating. And that's 2.63. 2.63. And 7 divided by 1.3333, repeating. That's the wrong one. And that's 5.25. And once again, the smaller organization is more likely to have this occur. And so the smaller is more likely. Oh no, what decimals did I not carry right? It has to be these. It has to be these. 5.25. It has to be this one. 7 divided by 2.666, repeating. Whoa. It's not that one. Oh, this was 3. How'd that turn to 4? Well, 8 minutes to get to class. I have no idea what happened on that one. How did I change that number? Think real quick. With the notation table. Yeah, exactly, Brock. It's lighter work with the notation tables. Really helps. See how close I can get on these. I might be able to get the top one. That's going to be $11.25. With $11.25, it's a very low probability. $11.25 is 235 above that. 235 above that. It's probably like a z-square of 2.3. So that's the top 1%. So like this. It's very close to this. Something like that. Total amount she earns on the best 1% of weekends. That's a z-square of... Oh, it's very close to this. Whoa. 11.25, so close to 450? Is that right? Something like that. Let's see how we did. 0. Was it not going to show me answers? No way. Why don't you show the answers? Does it not do that anymore on me? For me? I don't want to... Because I check answers, it goes wrong. Well, darn it. With that, we're going to head off right here. It's time for class. That's skewed to the right. I almost got all of them done. Approaches normal shape. The variability in the means stays the same. The histograms are fairly normal. The variability decreases. That should do it. There we go. Do we only not do 2 of these? No, 3. Very similar. Well, that's skewed to the left. These simulations do support. The peak stays about the same. The shape becomes more normal. And the variability in the means decreases. That's sigma over square root of n. The rule of thumb does not hold. It doesn't apply for highly skewed. Well, what? It's not a rule of thumb. What's up, Preston? Good to see you here. Oh, I put variability increases sigma over square root of n. Sigma over square root of n. With that, it's time for class. Bye for now, everyone. Bye.